So in last video we had seen measurement of HV DC voltages, okay, where we studied the series resistance microammeter, resistance potential divider and the generating voltmeters. This video will start with measurement of high AC and impulse voltages. Okay, so if you go through the slides, okay, so here you can see measuring AC voltages with power frequency and impulse voltages consists of series impedance emitters, resistance or capacitance potential dividers, the potential transformers, electrostatic voltmeters, sphere gap measurement, peak voltmeters, okay, and potential divider with cathode ray oscillograph. So we'll see all this in today's video, how to measure HV, AC and impulse voltages. Okay, so first we'll see this was your generating voltmeter and these are the advantages, disadvantages, right? So measurement of high AC and impulse voltages. So here first we'll see series impedance voltmeter. So here what we had done in last measurement of HV DC is we used a generating voltmeter. Okay, but here in measurement of HVAC and impulse voltages, these measurement of HVAC voltages employ some conventional methods. Okay, as I told you, the first method is series impedance voltmeters. Second, we will see the potential dividers, resistance and capacitance potential dividers, and we'll also see the potential transformers, or also called as electrostatic voltmeters. Okay, so but if you talk about the designs of this type of measurement, okay, these designs are different from those of low voltage emitters. Okay, as the insulation design and the source loading effects are important here. Okay, since we are measuring high voltages, right, the insulation design has to be taken care of, and the source loading also should be taken care of. Okay, so first we will see series impedance voltmeter. For power frequency AC measurements, the series impedance voltmeter may be a pure resistance or a reactance. Since resistances involve power losses, often a capacitor is preferred as a series reactance. So, moreover, for high resistances, the variation of resistance with temperature is a problem, and the residual inductance of the resistance gives rise to an impedance different from its ohmic resistance. So, if we are talking, right, the high resistance units for high voltages have stray capacitances. Okay, these have stray capacitances, and hence a unit resistance will have an equivalent circuit. Okay, this would be an equivalent circuit. So at any frequency omega of AC voltage, the impedance of the circuit, impedance of the resistance R, right, is given as Z is equal to, see, R plus j omega L, since these two are in series and the whole combination R plus L combination is in parallel with C. So R plus j omega L divided by 1 minus omega square LC plus j omega CR. Okay. So this is the impedance of the circuit, where L is residual inductance and C is the residual capacitance. Now, if omega L and omega C are so small to R, right, then this equation, let me say this is my equation 1, Okay, then this equation can be reduced to Z is nearly equal to R into 1 plus J omega L by R minus omega CR. So now see, this is my total impedance, okay, magnitude. How about the phase angle? The total phase angle is given by tan phi, which is omega L by R minus omega CR. Okay, now this can be made 0 and independent of frequency. Okay, if L by C is equal to R square. Okay, so if L by C is equal to R square, right, the phase angle here, that can be made 0 and can be made independent of the frequency. Okay, now if we go for large, if these resistors which we are using here, okay, these are large. Okay, so for extended and large dimensioned resistors, okay, this equivalent circuit is not valid. Okay, and each elemental resistor has to be approximated, okay, with this equivalent circuit. Okay, so the entire resistor unit here has to be then taken out as a has to be taken as a transmission line equivalent. Okay, we have to take it as transmission line equivalent for calculating the effective resistance. Okay, also the ground or the stray capacitance effect of each element, since it has the effect, it influences the current flowing in the unit. Okay, and the indication of the meter, it results in an error. Okay, therefore we have to go for some other equivalent circuit. Okay, so the equivalent circuit of a high voltage resistor neglecting inductance and the circuit of compensated series resistor, right, using guard and the tuning resistors can be seen in your figure A and B, which I have shown here. Okay, so by tuning the resistors, right, you can see here the resistor RA. Okay, here at the top, at the HV terminal, you have the resistor RA. So by tuning the resistors RA, the shielding resistor and the potentials, okay, may be adjusted. Shielding resistors, okay, are your guard resistors, which can be seen here. Okay, RA is the tuning resistor, which you can see at the top. It's a variable resistor, and R is the series resistor. Okay, however here, if you remember transmission line equivalent, okay, CS was our winding capacitance and CG was the stray capacitance. Okay, capacitance to ground. So by tuning resistors RA, it means the topmost resistor, the shielding resistor and the potentials may be adjusted with respect to actual measuring resistor, so that the resulting compensation currents between the shield and the measuring resistors provide a minimum phase angle. Okay, so this part is important here. Okay, so this is all about the series impedance voltmeters. Okay, so similar to series impedance voltmeters, we have series capacitance voltmeters also. Okay, so now to avoid the drawbacks, okay, pointed out in series impedance voltmeters, what we do, a series capacitance voltmeter is used, where a series capacitor is used instead of using a resistor for AC high voltage measurements. Okay, I hope that is clear. The current IC through the meter, okay, the current IC through the meter, I'll give you a figure first. Okay, see, this is the figure. Okay, so the current IC flowing through this meter is J omega C into V, where C is the capacitance of series capacitor, omega is angular frequency, and V is the applied AC voltage. Now, if the AC voltage, if the AC voltage contains harmonics or errors due to changes in series impedance occurs, the RMS value of the voltage V with harmonics is given by, we all know the formula for RMS value. RMS stands for root mean square. So, V is equal to square root of V1 square plus V2 square plus so on up till Vn square. Where your V1, V2 and Vn represent the RMS value of the fundamental, the second and the nth harmonics. V1 is the fundamental, RMS value of fundamental harmonic, right? V2 is of the second and harmonic, and Vn is the RMS value of voltage of nth harmonic. Now similar to voltage, the currents due to these harmonics can be given as I1, because of V1 I1 flows, which is given as omega C into V1. Due to V2 I2 flows, which is 2 omega into CV2. Due to Vn the In flows, n omega into CVn. So with this we have to calculate the resultant or total RMS current. Hence the resultant RMS current is given as I equals to, from these three equations I have taken omega C out. So I am left out with V1 square plus 4 into V2 square plus so on up till n square Vn the whole square. Right? This is all either under square root or I am taking power 1 by 2. So, see, with a 10%, if you consider 10%, so with a 10% of fifth harmonic only, 10% fifth harmonic only, the current is almost 11.2% higher. Only with 10% fifth harmonic, the current goes to 11.2% higher. And because of this the error is 11.2%. Current value and the error goes high. That is why this method is not recommended when AC voltages are not pure sinusoidal waves. But if it contains harmonics, then only it is considerable. Instead, series capacitance voltmeters, what we are talking here, were used with the cascaded transformer for measuring RMS values up till 1000 kilovolts. So the series capacitance was formed with the help of two parallel plates, as a parallel plate capacitor between the high voltage terminal of the transformer and a ground plate suspended above it. And a rectifier emitter was used earlier as an indicating instrument and was directly calibrated in high voltage RMS value. So that is why, because of this error in the reading, we do not prefer series capacitance voltmeter. I hope up till here it was understood, right? The next method what we will discuss is the capacitance potential divider and the voltage transformer. Capacitance potential divider and the capacitance voltage transformer. Now the errors due to harmonic voltages can be eliminated by the use of capacitance voltage dividers with an electrostatic voltmeter or a high impedance meter. We can use a high impedance meter such as TVM. We have TVM. Now, if the meter is connected through a long cable, its capacitance has to be taken into account for calibration. Okay, we have to go for calibration. Hence, usually a standard compressed air or gas capacitor is used, okay, as C1. Okay, here for C1 we generally go for a standard compressed air or gas capacitor, okay, and C2 may be a large capacitance, and to C2 through shield, you can see the shielding through a shielded cable, and C2 is completely shielded in a box to avoid stray capacitance voltage transformer. Okay, so you can see the shielded cable. Okay, this is your shielded cable and this is the shielded box. This is to avoid stray capacitance voltage transformer. Okay, so this you can see. Yeah, this is the figure. Let me clear it out. Okay, this is the figure where C1 is the standard compressed gas high voltage capacitor, C2 is standard low voltage capacitor, ESV what you are seeing here is the electrostatic voltmeter, P is the protective gap formed. I told you in last 1 meter we had considered the paper gap. Okay, it's the protective gap, and CC is my connecting cable. Okay, CC is my connecting cable. Now here we have to check what would be the applied voltage. Okay, now the applied voltage V1 is given by V1 equals to V2. So you can see here the figure, right? You have C1, C2 and right, you have ESV, okay, and the ESV is your meter. Okay, so meter is itself having some capacitance. So see here I have taken V1 is equal to V2 into C1 plus C2 plus Cm divided by C1. Okay, where Cm is the capacitance voltage transformer of the meter what we have considered and the connecting cable and the leads, and V2 is the meter reading. It means Cm is the total capacitance of this meter plus the connecting cable which we are seeing here and the leads. Okay, this connecting cable and the leads which we have. Okay, capacitance is Cm. Okay, and V2 is the meter reading. Okay, ESV ka meter reading. Now capacitance divider with a suitable matching or isolating potential transformer tuned for the resonance condition is often used in the power systems for voltage measurements. Now this is often referred to as CVT. Okay, now we are discussing capacitance voltage transformer. Okay, we are discussing capacitance voltage transformer. Okay, so capacitance voltage transformer means what? A capacitance divider. Okay, it's a voltage transformer. So a capacitance divider with a suitable matching or isolating potential transformer tuned for resonance condition is often used. Okay, so this is often referred to as CVT, right? Now in contrast to simple capacitance divider which require a high impedance meter, okay, which we have seen, or an electrostatic voltmeter, the ESV which we have seen, okay, which was here. You can see a ESV here. Okay, so in high impedance or electrostatic voltmeter, a CVT capacitance voltage transformer can be connected to a low impedance device like a wattmeter pressure coil or a relay coil. Okay, so CVT can supply a load of say few volt amperes. Okay, so I'll show you the figure. just a minute. Okay, somewhere here. Okay, see, this is the figure of a capacitance voltage transformer, okay, and its equivalent circuit. Okay, so you can see here I have C1. So C1 is made up of few units of high voltage capacitors. Okay, so if you consider this total C1, so total capacitance voltage transformer will be almost equal to few thousands of picofarads. Okay, thousands of picofarads. Okay, then you can see we have a matching transformer which is connected between the load. Okay, this is my matching transformer which is connected between the load or the meter M and C2. Okay, this is your matching transformer which is connected between either the load or M and C2. Okay, now the ratio of this transformer is chosen, just a minute. Okay, okay, right, see here you can see C1 is made up of few tons of high voltage capacitors, and the total capacitance transformer will be around a few thousand picofarads as against a gas filled standard capacitor of about 100 picofarad. Okay, now a matching transformer is connected between the load, what I showed you, or meter M and C2. The value the value of tuning choke L, you could see a inductor choke L is chosen to make the equivalent circuit of CVT pure resistive or to bring resonance condition. Okay, and I was talking about the ratio, transformation ratio. Okay, so the transformer ratio is chosen, transformer ratio of the matching transformer is chosen on the economic grounds. Okay, and the high voltage winding rating can be up to say 10 to 30 kilovolt. Okay, high voltage rating can be 10 to 30 kilovolt. However, low voltage winding rating has to be between 100 to 500 volts. Okay, now for the resonance condition, we know that W omega into L plus LT should be equal to 1 divided by omega into C plus C1. If it satisfies this, then see this condition is satisfied if this equation is true. Okay, where L is inductance of the choke coil, LT is equivalent inductance of transformer. Okay, referred to high voltage side. Now this is all about the construction of a CVT. Now we will see what are the advantages and disadvantages of this CVT. Okay, first advantage of this is it is simple in construction design. Okay, and very easy to install. Second is it can be used both as voltage measuring device for the meter and relaying purposes, and also as a coupling condenser for power line carrier communication and relaying. Right. The next advantage is its frequency independency. So frequency independent voltage distribution along elements as against conventional magnetic potential transformers. Next advantage the CVT provides is the isolation between high voltage terminal and the low voltage, right, because we have a matching transformer there. Right. Now talking about the disadvantages of a CVT, the very first disadvantage is the voltage ratio is susceptible to temperature variation, and the problem of inducing ferroresonance in power systems can be seen if we go for a CVT. Okay, so I hope up till here it was understood, right, and this is the figure of a CVT.